Welcome to this lecture on the basics of integration, presented once again by EDU Onyx. Today we're going to be talking about integrals in the context of machine learning. And integrals are going to be very important as soon as we dive into probability theory and some of the probability distributions that are produced as outputs from machine learning algorithms. So we're only going to be covering the basics. We're not going to be talking about very many of the rules. Again, just like derivatives, we could spend days on just the rules for integrating different types of equations, but we're not going to do all of that. We'll talk about some of the basic rules, but in general, we're going to focus more on the concept. And for that purpose, we have our nice little jet engine theme here. So let's dive in. The integration concept. Integration is used to find the area under the curve. So this is actually going to be the reverse process of differentiation, which is derivatives. So as a result, integrals are often called the antiderivative. So instead of finding the slope of the curve, what the integral is going to do is it's going to find the area under the curve. So this is a little bit different, and it's not immediately intuitive how this could reverse the derivative. However, if you think about this and perhaps the physical concept of the derivative, if the derivative of a displacement equation told us the velocity, then if we took the integral over velocity, we could figure out how far that object went. So perhaps we took the integral from time 0 to time 10, and if we had an equation for velocity, the integral would tell us how far that object went in that time. So you could think about it from that perspective. When you're plotting out the velocity graph, the area under that curve is going to be the displacement. So that is why it's the reverse of differentiation. All right, so some of the types of integrals, we can have indefinite integrals and definite integrals. So indefinite integrals are going to be integrals with no limits. This is when we're going to be taking the integral from negative infinity to positive infinity. So every single bit of this curve is going to be considered. Definite is going to be integrals with limits like the example I just gave you. If we were taking an integral from time 0 to time 10 seconds, that would be a definite integral since we're only concerned with a particular section of the curve. So these are going to be written like this. Integrals are this nice squiggly line here in the front. So the integral of f of x dx is going to be saying the integral of f of x with respect to x. And if there's no limits written on that squiggly line, that is going to be an indefinite integral. If we do have an a and b limits, that's going to be the integral from a to b. So point A to point B. You can do these in a couple different directions. So it's just going to be that particular section of the graph that we are concerned about. Again, the dx denotes the variable that we are interested in. You can have dx, you can have dy, you can have d, whatever variable that you are using in the integral. So we have these two types, indefinite and definite. They're going to be used in different concepts. So we'll talk about a few of those now. And again, the integral is most easily understood in the perspective of the antiderivative, in my opinion. So integration reverses differentiation. So we wrote that in this equation, we show the integral of f prime of x is going, with respect to x, is going to be equal to f of x. So remember, f prime here is the derivative. So if we take the integral of the derivative of a function, we're going to get back the original function. Also note this c here. This is referred to as the constant of integration. And it's there because, well, the derivative of a constant is 0. If you remember from the previous lecture on derivatives, whenever we have a constant and we take the derivative of it, it simply drops out because there is no rate of change to a constant. So if we took the integral, we actually have no way of knowing whether or not there was a constant tacked on to the end of this equation. because the derivative of, let's say, x squared plus 6 is going to be exactly the same as the derivative of simply x squared, or maybe x squared plus 2, or x squared minus 3. All are going to have the same derivative. That's why when we take the integral and we're going in the reverse direction, we have to tack on this constant of integration because we don't know whether or not there was a constant out there. So this is the integral in the context of the antiderivative. So let's talk about a few of the basic rules of integration. First, we have the power rule for integration, and this is going to be the reverse of the power rule in derivatives. If we have x to the n, so the integral of x to the n dx, what we're going to do instead of subtracting from our exponent now, we're going to add 1. So we have x to the n plus 1, and instead of multiplying in the front, we are going to divide, actually. So instead of a multiplication, we have a division, and it's going to be n plus 1. So you can think of it as multiplying by the reciprocal, if you will, or division. Either one's work. And again, we have that constant of integration tacked on to the n here, since we don't know whether or not this function had a constant there. So we have x to the n plus 1 divided by n plus 1 plus our constant of integration. So if we had an example here, the integral of x squared dx is going to be equal to x to the third, since we have 2 plus 1 on the top, multiplied by the reciprocal, we're going to have divided by 3, and then plus our constant of integration. And note that these are indefinite integrals at this time, so we're not evaluating them over our particular section. We can handle constants in integrals pretty easily, and this is actually going to follow the power rule if you think about it carefully. If we have the integral of, let's say, some constant k with respect to x, we are just going to be adding on an x to that constant. And then once again, we have our constant of integration tacked on to the end. So let's look at an example. The integral of 4 dx is equal to 4x plus c. And this makes sense. Why? Because, well, just 4 is the same as 4 times x to the 0th power, since x to the 0th power is just 1, of course. So if we had our power rule now and we had n is equal to 0, n plus 1 is going to be 1, so we get an x to the first back out divided by 1, so we're just left with the x. And so really the constants is going to be the same as following the power rule with x to the 0th power. All right, so those are the very, very basics. And once again, there's tons of the rules for handling different equations out there. We're not going to worry about them too much. But we are going to talk about evaluating definite integrals. So if we have limits now on our integral, let's say from a to b, we are going to have to evaluate those when we solve for this integral. So this is the same as saying the value of f of x plus c at x equals b minus the value of f of x plus c at x equals a. So those are our limits there. And this is typically since, well, the c's are going to cancel out since we have those on both sides of our subtraction here. We have a c minus c. So we're really left with just f of b minus f of a. And this is typically written with this vertical bar here. So if we have the integral of f prime of x dx from a to b, we're going to write that as f of x bar a to b, which is going to be the same as simply plugging in those variables. You do the top coefficient first, so f of b minus f of a. So let's go ahead and look at an example for that, because that's kind of hard to follow. So if we were to solve the integral of 3x squared dx from 0 to 2, we'd start by taking the integral. We have the constant 3 there. We can move that out in front of the integral just like we did in the derivatives. So we now have the integral of x squared dx. Taking that, following our power rule, we're going to get x to the third over 3 bar 0 to 2. So our 3's are going to cancel out here. So we're left with simply x cubed. Plugging in our two values here, we have 2 cubed, which is going to be 8 minus 0 cubed, which is, of course, 0. So we're left with a grand total of simply 8. And so this is actually going to be the area under the curve of 3x squared from 0 to 2. That's what we just found here since we are taking the integral. So thinking of this as in the context of being the area under the curve is a good way to understand definite integrals since we are looking at a particular section of the curve. All right, and this is called the basics of integration because we are truly just doing the basics. We'll talk about these more in probability theory when they actually come up with probability distributions and what integrals mean in the context of probability distributions. But for now, we're going to move on to other parts of calculus because integrals aren't essential for convex optimization, which is ultimately what we're building up to in this unit. It's how we optimize the neural networks or machine learning algorithms in general. So we're going to focus on that a little bit more in this unit. But just keep these basics in mind and we will return to them later in this course. Thank you very much for listening.